Welcome back. Today we're going to be looking at similar figures and using those similar figures and their properties to find missing values of x. So we are going to be working on a set of similar figures that are triangles and a set of similar figures that are rectangles. But before we can do that, I want to go back to Unit 5 and talk about the things that we learned about Unit 5. So, Ziva wants to say hi. Hi, Ziva. Hi, Z. Okay, now we can learn. So in Unit 5, we looked at, first we plotted some stuff because we were moving some figures around the coordinate plane, so we had to practice plotting points. And then this is what we made together. These are the four major transformations that we talked about. So the first one we talked about was translations. We can take a figure and we can shift it anywhere we want on the coordinate plane, and it ends up being congruent. So it does not change size, doesn't change shape. With a translation, it doesn't even change orientation. It just stays exactly how it was. We just physically moved it around. So we wrote that on the inside. We said we're just shifting the figure on the coordinate plane. Size, shape, and orientation stay the same. Location is different. So that was the first one. Then we looked at reflections. So we had this mirror image, and we reflected something over that mirror image, just like when you look in the mirror. So when we looked at all these details, we said its definition was that it's a mirror image across an axis of symmetry on the coordinate plane. That axis does not have to be the x-axis or the y-axis. Remember, we came across a couple that were really tricky where it was being reflected over a line, and you guys didn't know how to graph lines yet. That's our next unit. So when we do these reflections, shape and size stay exactly the same. They are congruent. The location and the orientation change. So that's reflections. Then we looked at rotations. In a rotation, we take an image and we physically rotate it. So this is where we use those little transparency sheets and we spun the transparency around. So in a rotation, we have a circular rotation about a fixed point. Size and shape stay the same, so again, they're congruent, but the orientation and location are different. So those were the first three. And then we moved on to dilations. Dilations is the one we want to focus on today, because this is the one that produces similar figures instead of congruent figures. So these three all were the same size and shape, but in a dilation, the size changes, but the shape does not change, which means these are similar. So we take something. We had a couple ways of doing this. We could either take its side lengths and multiply them by a scale factor, or we took the actual ordered pair and multiplied its values by a scale factor to get the new one. But either way, we ended up with a shape that's just bigger by some scale factor or smaller. So we defined it saying that a dilation changes the size of a figure by a scale factor. Shape and orientation are the same. Size is different. So that's the one we're going to focus on today. So when we dilate a figure, we create similar figures. Sometimes we know that scale factor ahead of time. Sometimes we don't, and we need to solve for it. So before we do our problems, let's just look through and save this from every class so nobody feels left out, well, except F block, I guess. So here was a practice we did on translations. We did a snowman. Remember, you guys had to reflect some things to make a snowman. This one's on reflections, rotations. We did our transformation soccer. This was kind of a tricky paper. It just had everything. Your emojis. I know there's a couple of you guys that still didn't finish emojis. These were hard. You can still do them by April 8th. We had some MCAS prep. You guys aren't taking MCAS this year, so you lucked out. And then the test. So this was everything you had to know, was those four transformations. So today we're focusing on this piece of it, those scale factors. So let's set something up. Here's my problems. So for the first one, I have a set of similar figures, which means they're same shape but different size. So I'm going to set up an equation and solve it. When you set up this equation, we can compare corresponding side lengths, meaning I could say that there's a ratio between x and 3 that's the same as the ratio between 4 and 2. So I could set up that as an equation, or we can just set up within one triangle has a ratio. So x over 4 equals 3 over 2. I'm going to set those equations up for you, but I just want to let you know you could do it either way. In this one, I'm going to do it within the same triangle. So I'm going to say this triangle has a ratio of side lengths, x to 4. This has to be, hi Henry, it has to be the same ratio as the smaller triangle. Even though it's smaller, it still has the same ratio of side lengths. So this is going to be 3 to 2. Now we have the equation. We have to cross multiply to solve this equation. So I'm going to give you all the equations in your practice problems today. You'll just have to cross multiply. So x times 2 is 2x. 3 times 4 is 12. We're going to set those things equal. And now we're going to solve our equation. Divide by 2 on both sides. And x equals 6. Which means this side length was 6 units. That makes sense because these are each double, right? Times 2 and times 2. Dear, stop making fun of me. All right, I have one more for us today. This one's a little bit more complicated. I set up the equation already, and the way I set it up, we have two rectangles that are similar, and rather than set up the ratio of side lengths within each figure, what I did instead is I did the corresponding side lengths. So I said x is to 3 as x plus 3 is to 12. So now I can solve this to find what x is. So over here, we're going to cross multiply. X times 12 is 12x. And x plus 3, I'm going to put in parentheses. I'm going to multiply it by 3. We're just going to set those two things equal to each other. Whoops. And now we're going to solve. So first thing we should do, since we have multiple steps here, let's draw our squiggle. We're going to distribute. So this becomes 3x plus 9. There's nothing to combine, so I'm going to rewrite the other side. And I'm going to move all my variables to the left. So I'm going to subtract 3x over. And I have 9x equals 9. And we're going to divide by 9. So that tells me that x is equal to 1. So back over here, that means this is 1. This would be 4. So now we can see this is 3 times bigger and 3 times bigger, so it makes sense. All right, good luck today.